you. So thank you for giving us the opportunity to present our talk at work. And our talk is about the plotting UCX for Tofu D interconnect of Fugaku, and this is a lightning talk. And I'm Yutaka Watanabe from University of Tsukuba, and I'm a graduate student at the university. So first I will explain about our introduction and the motivation for our work. And the first one is the explanation of the Tofu D. And the Tofu D net interconnect net is a 6-dimensional virtual truss network interface, which is used in supercomputer Fugaku or Fujitsu FX1000 based systems. And Tofu D interconnect is integrated in Fujitsu A64FX CPU chip, and the A64FX chip is an ARM-based many-core processor. It has 48 compute cores and 2 or 4 assistant cores. So compute core do the computation, and the assistant core process the OS threads. OS around process or around the OS. So, and if we want to use Tofu network from user land, Tofu API is provided by Fujitsu, and Tofu is the lowest level of API to use Tofu from user land. So, and also we have Fujitsu MPI, which supports the Tofu natively. So if we have a program written with MPI, then we can just compile with the Fujitsu MPI to run on the Fugaku. So the right above figure shows the block diagram of the Tofu network interface or Tofu interconnect. And we have 6 TNIs. TNI is a kind of RDM engine. And one TNI has a capability of 6.8 gigabyte per second bandwidth. And we have 6 TNIs. So the aggregated bandwidth is 40.8 gigabyte per second. However, if we have a program that is written with UCX, we cannot fully utilize the performance of the Tofu network because UCX does not support the Tofu interconnect natively. Actually, we can run with a TCP protocol because Tofu supports TCP or IP or over Tofu. So we can use a TCP on Fugaku, but if we use the UCX with TCP protocol on Fugaku, the performance is not good compared to the theoretical performance of the Tofu network. So we need to port the UCX for Tofu to enable to achieve better performance with on Fugaku with UCX. So this is one of the motivation. So we want to utilize the UCX system on Fugaku or other system using Tofu. And the another motivation for us to for this folding is that we are planning to make a task-based distributed programming framework with UCX. So the task parallel model is our kind of parallel programming model that a program is divided into the set of tasks. So a program is constructed by a lot of tasks and build a task flow graph or a dependency graph like this middle figure. And then each task will be executed asynchronously following the task flow graph. So especially compared to the traditional data parallel model, which does the same operation to the different data using a lot of cores, especially for many core processors. If we use the data parallel model, then we sometimes need to do a global synchronization among cores. But especially if we use the many core processors, the cost of the global synchronization among the cores is expensive. So the benefit of the task-based programming is we can avoid the global synchronization, and we could have a potential to fully utilize the many processors if we can write a efficient program with a task-based parallel model. So that's why we are focusing on this model. And the task-based distributed programming model is extended model of the task parallel model to the with clusters. So we want to process a single task flow graph with a lot of nodes. So this lower figure shows the overview of the task-based distributed programming framework. So, and we have in this, this is a simplified figure. So we have just two nodes and some threads on the node, and each thread on node process the tasks asynchronously. And if we need to do the data movement between nodes, for example, if the node one task needs data that exists on the node 0, then we will do the data copy using the one-sided communication. And so by doing the one-sided communication, the framework will resolve the data dependency, and the task on node 1 will be executed. So this is an overview of the task-based distributed programming model. And so in this framework, we want to use a UCX as a lightweight low-level communication layer, because we just need a lightweight one-sided communication. So we want to UCX rather than MPI because UCX has less overhead than MPI. And also, some implementation of the NP has a problem with multi-threaded environment. So we want to control by using the lower level API with UCX. And also, it's a benefit for us if we can build the framework with UCX, then we could have a potential to run on the different interconnect networks. Right, for so like InfiniBand or ROC. So this is also a benefit. The portability is a benefit for us. So next slide is two kind of evaluation. We did two kind of evaluation. And first of all, I will explain about the left-hand side. This figure shows the boundaries of the UCX, original UCX with TCP protocol on Fugaku. And we compare the result with Fujitsu MPI. And because we couldn't use put one-sided API on Fugaku using with TCP protocol, so we use the tag message API to compare the measure and compare the performance of these two kinds of libraries. And if focusing on the MPR, the boundaries of the MPR, the MPR scales as the message size increases, and this is an expected result. And at the maximal largest message size within this range, we could achieve 6.2 gigabyte per second at 4 kilobyte messages. However, if we focus on the boundaries of the UCX with largest message size, we could only achieve only about 170 megabytes per second at 4 kilobyte messages. So this is just one evaluation of the TCP protocol with UCX, but it obviously shows that we need to put UCX for Tofu D if we want to achieve the better performance with UCX on Tofu D network. So, and the right here shows our ongoing work, and at the moment we submit our work to the UCF meeting, we could able to run the UCTs, zero copy API to the API without UCX for Tofu D implementation. So, and we compare the UCTs on UCX performance with NPI, and also we compare that with UTOF. So we compare the three kind of libraries using put API. And first of all, if we focusing on the smaller message size, UCX has some overhead compared to the UTOF. But this is because we wrapped the UTOF API with UCT, and this is expected overhead. But we want to see if we can improve this overhead. Right. And if we focus on the scaling of the UCX and UTOF, both scales well, and the scale both scales similarly. However, if we compare these two to NPI, NPI does not scale well compared to the UTOF or UCX, and this is because we need to do the window lock operation in the NPI due to NPI's semantics. So this results the performance difference between these two. So this is one of the reasons why we want to use UCX or UTOF in our plant Kasky-based distributed framework. And if we focus on the maximum bandwidth, maximum largest message size, the performance boundaries of these three is almost same. That is about 6.3 gigabytes per second, but UCX or UTOF is slightly better than NPI. So this is a preliminary evaluation with our preliminary implementation, but it shows that we have a potential to use Tofu D. We have a potential to achieve a good performance of the Tofu D using a UCX. And this slide shows our current status of the feature work of this work. And for the current status, we are not implementing the Active API, Active Message API, or UCT for Tofu D network. And we are to continue the implementation until the OpenShimen works correctly with UCX on Tofu D. And our future plan is that we want to do the scaling test using a supercomputer Fugaku, which has Fugaku has about 150,000 nodes, over 150,000 nodes. So it's a good environment to test if the UCX for Tofu D scales well or not. And at this moment, we haven't done any scaling tests, so we need to do this once our implementation is finished. And we also want to do the optimization of the implementation for Tofu D and based on the performance evaluation. And also we want to do the implementation of the task-based distributed programming framework with UCX for Tofu D network. Thank you for listening.
Okay, thank you for your presentation. Do we have any questions?
I have one question.
Yes, Pasha.
The 20% overhead on small messages, do you guys have any idea what contributes to the overhead of 20%?
Actually, I'm not sure how the overhead comes from, but I think our implementation of the flashing the queue is not good, I think. So I think by improving the method to flash the queue, I think we can achieve more. I think we can improve the performance.
Okay, and another question is if you guys have any plans to upstream this to UCX main project at some point?
Actually, I didn't thought about that, but yeah, if our implementation is good enough and our implementation is good enough to push the mainstream, then it's a good thing to I am happy to push our implementation to the mainstream.